Hello everyone, I'm Eric Augustine from the University of California at Santa Cruz, and today I'm going to be presenting the work, Collective Grounding, Applying Database Techniques to Grounding Template Models. This is joint work with myself and Lisa Couture. So as we know, machine learning has been hugely successful and has been widely impactful across many different fields. Text-to-speech, computer vision, natural language processing, all over we see machine learning successes. But if we look at that success a little deeper, we actually see a lot of very difficult problems. In fact, what I'm showing here are not successes of machine learning, but these are actually failures. I'm showing a neural model failing to provide an adequate explanation as to why an image is a wolf versus a dog. I'm showing a neural model being tricked by an adversary into thinking a panda is a gibbon. I'm showing sexist and biased word embeddings. I'm showing an image classifier falling flat when provided with noisy labels. In all these situations, we see these very difficult problems in machine learning. And one way to address kind of each and every of these problems is by adding structure or adding relational information to the problem. We could have some sort of structure to provide some sort of explanations for us. We can use relational information to overcome adversarial attacks. We can enforce fairness constraints onto embeddings. We can provide or integrate knowledge bases into computer vision models so that they don't fall flat when provided with noisy labels. In all these situations, kind of bringing structure into the problem really helps. And the general family of kind of bringing structure into the problem is called structured prediction. And a general kind of class of techniques within structured prediction is called statistical relational learning, or SRL. Now in SRL, the general idea is we're going to combine the sort of relational structure with statistical inference. And generally, how SRL frameworks work is they're going to take some sort of templated rules, usually in the form of first-order logic, and combine that with some sort of kind of graphy relational data to create a probabilistic graphical model. And then once you have a probabilistic graphical model, well, then there's all sorts of inference methods you can do over that. And that's great. But unfortunately, there's kind of no free lunch. This doesn't just solve our problem. In structured prediction, whenever we're kind of introducing some sort of dependencies between predictions or dependencies between predictions and observations, what we're really doing is we're lifting the independence assumption from our machine learning. And when we do that, we're going to incur a huge computational burden. And in SRL, this computational burden is typically paid during a process called grounding. So I'm going to give you a little overview of grounding in statistical relational learning, just enough so that you can understand kind of the rest of this paper. So grounding in statistical relational learning, or SRL, is the general process of taking the logical rules I mentioned before and combining those with actual data to create our graphical model. So you can think of it, it's not about solving our problem, it's actually just about formulating the problem. And in SRL, typically what we do is we start with our rule. So here we have a logical rule that would be used in, say, a recommender system. And then from that rule, we want to create a query. And because the query is being created from kind of this sort of logical rule, it's pretty simple. If we think of each logical predicate as a relational table, then it's pretty straightforward to create a query from a rule. So we create a query, and then we execute the query. And what we're going to execute is a query that gives us the replacements of logical variables to concrete data, to actual data we see in our database. And that's great. And then each result is actually going to represent kind of one instantiation of that logical rule. We call these ground rules. And then the collection of these ground rules, well, each ground rule is going to represent a clique in our graphical model, so the collection represents our entire graphical model. So that's the general process of grounding in SRL. And now I'm going to kind of show you some of the milestones in scaling in SRL to really show you kind of how impactful grounding is on the overall process. So to start out in 2007, we had one of the first big SRL frameworks called Alchemy. This is based on Markov logic networks, or MLNs. And it was able to ground a program of about 1 million size in a bit more than 6 hours. And it spends almost the entire time, 96% of its time it spends grounding. One thing to note is that all the numbers in this table, these are all recreated on modern hardware. So this 6 hours is not 6 hours in 2007. This is 6 hours in 2023. So next, in 2011, we have Tuffy, which is also based off Markov logic networks. And Tuffy really did a lot of work on grounding and systems, kind of the scalability of SRL. It set forward kind of all the grounding mentality that we use going forward. And because of all that work, it greatly improved the runtime and especially grounding time in SRL. So it brought it up to being able to do a program about 2.5 million times in just about 2 hours. And it still spends about half of its time grounding, which is still very substantial. And then we have a framework called FoxPSL. So this one is a distributed framework. So there's a little bit of apples and oranges here. And it's distributed over 4 servers, but it still spends about a third of its time grounding. And then we had a real big breakthrough in 2011 with PSL 2.1, or probabilistic soft logic. And it kind of was able to do programs that were an order of magnitude larger faster than the previous programs. But because its inference is very, very efficient, that means almost all of its time is spent grounding. 99% of its time is spent grounding. Then in 2011, it was able to improve upon that and make it even faster, but it still spends 40% of its time grounding. So still, a very large amount of time in SRL is spent grounding. So if we want to kind of improve the speed of SRL, grounding is a definite place to look at. So now I want to talk a little about how all the frameworks on here ground. We talked a little bit about kind of the individual grounding process of one rule, but how does it ground entire programs? Well, what it does, and all the frameworks on the list do the same thing, is it's going to look at one rule and it's going to ground out that rule, and then for the other rules in the program, it's just going to do them sequentially. It's going to take them one at a time and just do each of them independently. So we're actually going to refer to this as independent grounding. And that's great, and this works well, and it's very simple to implement. But the problem is that there's some things here that we can potentially exploit to improve grounding speed. Specifically, if we look at multiple rules, what if we had two rules that when they ground, they produce queries that have the same result sets? Well, if they have the same result sets, then what if instead of doing two queries, what if we could recognize this and only do one query to ground them both? Or even something that's more interesting and more complicated, what if we had a third rule that produces a superset of the results that we see in these first two rules? If we do that and we can recognize that A is a superset and B, here are kind of these extra ground rules that we can toss out for the first and second rules, then we could potentially even just do one query and ground our entire program. And this is the real key concept behind the work I'm going to be discussing today, collective grounding. Like I said, the general idea is what we're going to do is look at our rules and try and find shared workloads that we can execute and share amongst all of these different rules. So I'm going to step through the general overview of collective grounding, but there's not enough time to jump into all the details. Please ask me later because I love all this stuff, and I'd very much love to answer whatever questions you have about the specific steps. So in general, what we're going to do in collective grounding is we're going to start out very much the same as independent grounding. We're going to take each rule and we're going to create a query from these rules. This is the exact same query that's used in independent grounding, and we're going to call these our base queries. Then for each base query, what we're going to do is try and generate a bunch of candidate queries or candidates. So a candidate query is just going to be another query that can be used to ground for that same rule. Now, you may be saying here, Eric, you're taking a base query and generating a bunch of kind of candidates or other queries from that you can also use. This sounds an awful lot like query writing, and you're right, this is query writing. But then you may also say, Eric, if you're doing query writing, just leave it to the database. Just leave the database engine, they're going to do it better than you. And you're right, but there's something special going on here. The special thing is that for a normal database engine, it kind of has data in, data out, and it has to produce the exact same results in any rewritten queries as the base query. But because in SRL, these queries, the results from these queries are not just data. We know that each result set is actually an instantiation of a logical rule. It's a logical expression that we can evaluate. To see whether or not it's kind of useful or not. So imagine what if we have a logical expression, we see that one of our ground rules creates a tautology, something that's always true, well, then we can just toss it out. That's not going to be useful in our inference process. So what I'm describing is kind of the exact same thing that we idealized just a couple of slides before. We can evaluate our ground rules to see if they're actually going to be useful, to see if they're going to be these extra ones. And what we can actually do is we can cut down all of these extra rules all these extra ground rules that may not actually apply to each specific rule we're grounding for. So this is exactly what we saw in this slide earlier. So what we can do is we can generate a bunch of candidates that are going to be slightly different than each base query. It's going to return, instead of returning the exact same result as each base query, it's actually going to return a superset of the results for each base query. And because we can evaluate each ground rule, we can throw out all the extra results. So then once we have all these candidates, what we're going to do is actually prune down the space a little bit. We're going to search through space and pick out the candidates that are most likely to be beneficial. This is a pretty involved process here, but I'm going to leave out the details for this talk. So then what we do is once we have all these candidates, we need to figure out what rules each candidate can ground for. Because of course we know that the candidate generated from rule 1 can ground rule 1, but can it also be used to ground for rule 2 or rule 3? And if we think about what we were just talking about before, what we're really asking is for each candidate, what rules base queries does it provide a superset of the results for? And you may also be saying, Eric, this sounds very familiar to some other database work. This sounds exactly just like query containment. And once again, you're right. This is the problem of query containment in databases. But just like with query writing, the structure of the problem actually gives us a little bit of an advantage. Because here, we know that our queries just aren't these random queries that we're getting submitted to us. We know that each query is generated from a logical rule. And we can know things about these logical rules depending on the exact framework we're using. Is it acyclic? Is it chordal? Does it emit a simple junction tree? All of these things would be able to drop down the NP hard problem of query containment down to polynomial time. So the structure of the problem, once again, gives us an advantage over kind of vanilla database work. So then once we have kind of what I call the containment mapping, the mapping of all the candidates to the rules it can ground for, what we need to do is now we need to select the subset of candidates we're actually going to execute. And once again, your database senses might be tingling because what we're doing is actually the database problem of multi-query optimization. We want to select kind of the subset of workloads to actually accomplish our task. So, and once again, because the structure of the problem, it actually is a little easier than a vanilla database problem, because instead of just kind of having set fixed workloads from a specific set of queries, we have all these candidates that we can choose from. What we're actually looking at here is a multi-choice discrete knapsack problem with replacement. So overall, this is kind of the process of collective grounding. And now I'm going to kind of jump into some of our experiments real quick. So for experiments, we do them over many different data sets. You don't have to know the details of all these data sets. The important thing to know here is that these are actual real-life data sets. We didn't kind of construct any just for this assignment. We didn't use any synthetic ones. We just picked real data sets that have been published before, and we used them without any modifications to either the data or the model. So we just use them straight up. And here we see some of the results. We see independent grounding in orange, and we see collective grounding in blue. And the results are roughly sorted from size of the program, so small on the left, large on the right. And it may be easier to, because this is in log scale, it may be easier to really see in kind of a relative setting. So now we see the results relative to independent grounding. And there's a couple really important things here. One, of course, across the board, collective grounding does better than independent grounding. So that's great, a perfect way to start. Then if we look at these really small programs on the left, we see collective grounding still outperforming it. And the real key thing here is that what the numbers I'm showing are total end-to-end runtime. So this includes all the planning time of collective grounding as well. So even when we include all the planning, collective grounding still runs faster. And we're going to see in a little bit why that's so, because it may seem a little unintuitive. But then if we look at data sets that are kind of medium size-ish but don't exhibit a lot of structure that can be exploited by collective grounding, we still see collective grounding outperforming. And finally, when we see large data sets that actually have structure that can be exploited, we see this huge speed up. So we see like a 5 times speed up, and that's just in practice. Like ideally, you may be able to run one query instead of, say, 100 queries. It really just depends on the data set. But here we see 5 times speed up easily. So if we look at kind of the reduction in the number of queries done for each data set, there's two that I really want to point out. So I'm going to start with this Last.fm data set that has, so there's a 1.6 times speed up and a reduction in the number of queries from 21 down to 3 queries. And Last.fm, the important thing to understand here is that this is a recommender system data set that's recommending music to users. And the idea behind recommender, there's kind of 3 core concepts that you see in almost every single recommender system model. And that's the idea of exploiting user-user similarity. So if there's 2 users that are similar and we recommend one user something, maybe we'll recommend the other user something. Item-item similarity. So if a user likes something, like some item, and we know there's another item that's similar, maybe we should recommend that other item as well. And finally, user-item pairing, which says there's some kind of inherent attributes between these users and items that facilitates a recommendation. So if we look at kind of the actual model used, you don't need to memorize this or look at it at all, but there's 21 original rules used here. And collective grounding narrowed that down to just 3 queries. But if we look closer, what we actually see is we see collective grounding recover the core concepts from recommender systems that we just talked about. We see 2 users and an item. We see a user and 2 items, and we see user-item pairing. So it recovered exactly what we were talking about before. And then for this next example, this is DDI, or drug-drug interaction, and we see it. We have 3.5 times speed up, but we see almost no change in the number of rules done, only 1 less. And DDI is drug-drug interaction, and what we're looking for here is kind of interactions between pharmaceutical drugs. And the key thing about this data set is it really uses a lot of similarities between these drugs to compute these interactions. So like if 2 drugs are chemically similar, or if they interact with similar proteins, similarities like this. And the original model is something like here. Here at the top, we see these sort of 7 similarity-based rules. In the bottom, we see 2 kind of administrative rules. I'll tell you right now, these 2 rules at the bottom are the ones that were merged. We really don't need to be worrying about these. But as an expert, when I looked at this, I said, okay, well, I think what it's going to do is reduce collective grounding is going to produce 2 queries, one for all the similarities and one for these 2 rules at the bottom, something like this. But what collective grounding actually did is it left all the similarity rules the same, and it just merged those 2 at the bottom. And of course, when I saw this very first thing, I thought was, dang, I got some sort of bug somewhere. I got to go fix this. So what I did is I ran collective grounding again, and I forced it to use the query plan that I came up with that went at the bottom. And what happened was collective grounding kicked my butt. It did way, way better than my forced sharing plan. Forced sharing did better than independent grounding, but collective grounding still did better than me. And if we look at this a little closer, we'll see that the plan I recommended actually produced a lot more results, like 3 to 4 times more query results that it had to chug through. And if we look even closer, what we see is that in the model it produced, it has all these similarities, but these similarities are all actually very sparse. So where I thought it should do 1 query, collective grounding says, I see the plan that you came up with, but I also see this alternative plan where I'm going to do all these joins with very sparse similarity tables, and I'm going to choose that instead. And you see collective grounding kind of taking the opposite choice as it did in the recommender system case. In this case, it decided to do more queries, but it still made the right choice because the queries it chose are very fast. So now that we kind of have all these results from collective grounding, we have to modify our kind of milestone table from earlier. We have to add in PSL with collective grounding. So now he was able to kind of improve the runtime of this specific model by 5 times. And kind of for the first time ever, we reduced our time spent grounding to under 10%, which is a pretty huge improvement. And I just kind of want to leave you with the idea of like, we saw kind of all the potential like really hard problems in in ML. And we can use structured prediction to solve all these problems, but it's up to us as kind of database people, as systems people, to go and provide the ML engineers with kind of the tools and the systems they need to produce them, to do these structured prediction methods fast enough. And that's about it. Thank you very much.